So we learned already about the density base. Now let's learn about the grid base. Grid. What does it mean by grid? We call this is grid because we have, let's say, a kind of shape like this one, and we want to make it smaller, and the small section we want to make it a kind of grid, or we call this is the multi-resolution. This is the multi-resolution grid data structure. There are some interesting methods like STING. It is the statistical information grid approach. Wave cluster using the wavelet method, and click. But click, we can mention this is a grid base, or sometimes people mention this is as a subspace clustering. So the STING, what is STING? This is an algorithm based on the statistical information grid approach. It has been proposed in this year, 97. So the spatial area is divided into rectangular cells. So if you have like this one, so this is the data in the I layer, you can have the upper layer. So you can make the aggregate resolution. You can also have another aggregate resolution, or you can have, this is the original or the first layer, and you can make it more detailed. So you can make a bigger one, more detailed, and you can also make another detailed layer. So there are several levels of cells corresponding to different levels of resolution. So this is the level of the resolution. Each cell at the high level is partitioned into a number of small cells in the next lower level. So the higher level is partitioned into the smaller one. So we have smaller resolution. And the statistical info of each cell is calculated. So the statistical info here is calculated, the statistical info here is calculated, the statistical info here is calculated, and stored beforehand, and is used to answer queries. So usually we can use this one to detect a kind of map. Parameters of higher level cells can be easily calculated from parameters lower level cells. So if I have this is the high level, and then I have the low level, like this one. Okay, so it means once I know this statistic information, I can extract into the higher level. For example, the count, or the mean, or the standard deviation, or the minimum or the maximum of value, and also the distribution. So I can know the distribution type, whether it is normal distribution or uniform distribution. Use a top-down approach to answer the spatial data queries. So top-down means from the top to the lower resolution. And then we start from a pre-selected layer, typically with a small number of cells. So if you have more detail, if you have more detailed resolution, then we can use the small cell here, and then we go to the next upper level, and then we go to the upper level to check what is the best clusters in this data. For each cell in the current level, compute the confidence interval. So this is one example. Let's suppose in the layer, in this layer, I have 4 cells. Okay. So the cell number 1, cell number 2, cell number 3, and cell number 4. So this is cell number 1, this is cell number 2, this is cell number 3, and then this is cell number 4. Okay. And for every cell, I have the information about n. N is the number of objects or number of points in the cell. So in this cell, there are 100 data. In this cell, there are 50 data. In this cell, there are 60 data. And in this cell, there are 10 data. M. M means the mean, okay, the average. So in this cell, the average is 20. In this cell, the average is 19.7. In the cell number 3, the average is 21, and in the cell number 4, the average is 20.5. S is the standard deviation. So this is the standard deviation for every cell. And then min is the minimum value of the attribute in the cell. So this is the minimum value for every cell. Maximum is the maximum value of the attribute in the cell. Okay, so this is the maximum value in the cell. The distribution is the type of distribution that the attribute value in the cell follows. Okay, so we know that the distribution in the cell 1 is normal, the distribution in the cell 2 is normal, the distribution in the cell 3 is normal, the distribution in the cell 4 is none. Okay, we do not know the distribution. Then, yeah, I can create the higher level. So after this layer, I can go to the higher level. How to go to the higher level? We can just aggregate everything. So the parameter for the parent cell will be n equals to 220. How can we get 220? It is the summation from all the cells. Okay, 100 plus 50 plus 60 plus 10. And here we have, because we have 4 cells, we want to extract into the higher level cell. Then all data will be accumulated. What about the mean? The mean, we know this mean. So we just gather the mean, and then we can get a new mean for a parent. What about the standard deviation? It's also the same. We can apply with the standard deviation for every cell, and then we can get the standard deviation of the parent. The minimum. So the minimum means I would like to check the minimum from the existing cell. So it is 3.8. And the maximum is 40, because this is the maximum from the 4 cell. And distribution. Because most of the data are distributed normal, it seems the parent will have also the normal distribution. Because if you look at this one, there are 210 points whose distribution type is normal. So how can we get this one? 100 plus 50 plus 60. So there are 210 points. The distribution are normal, but only this cell, the distribution is normal. So in this kind of algorithm, we can do something better. So we can do the analysis. For example, we can remove the irrelevant cells for further consideration. The irrelevant cells means, yeah, if the cells is not important, or if the cells have no proper distribution, the distribution is different from different cells, then okay, we can remove it. When finished examining the current layer, proceed to the next lower level. So you can go to the next lower level. Repeats this process until the bottom layer is reached. Okay, so if we have already the aggregation, we have the 4 layer. Yeah, if suppose we have another layer, then yeah, you will analyze until the most bottom layer. The advantages of this kind of analysis, it is query independent, easy to parallelize, and it is incremental update. And the computational time is OK. K is the number of grid cells at the lowest level. So if it is the parent, we have only one cell. If it is, for example, the second layer, we have 4 cells. And then we can go until K layers. So in the K layers, we have the, for example, K number of grids. Then, okay, we just calculate until K times. The disadvantages, all the cluster boundaries are either horizontal or vertical, and no diagonal boundaries is detected. So if you want to see this cell, the detail of the cell is vertical, or you can compare with the next cell, which is horizontal, but no possibility for diagonal like this one. There is another method for clustering, we call it click. So this is a method from this word, clustering in Quest. It has been proposed in 1998. So it is automatically identifying subspace of a high dimensional data space that allow better clustering than the original space. So click can be considered as both density and grid base. So do you still remember density? In the density, we want to find the group of data. We want to find data points that are in the neighborhoods. The grid base is something related to the distinction of the data into grid or cell. It partitions its dimension into the same number of equal length interval. So if I have data like this type, this thing, okay, the data is from 0 until 20, for example. So I can split, or I can partition the data into same number equal length interval. Maybe I can mention that this is 0 until 5, this is until 10, then this is until 15. Okay, so it is equal. And then it partitioned an m-dimensional data space into non-overlapping rectangular units. Okay. So the idea is the same like this one. We want to make one rectangular, one rectangular, one rectangular, okay, different rectangular in the data space. a unit is dense if the fraction of the total data point content in the unit exceeds the input model parameter. So if I have the data, if the data here is many, okay, then I can say this is dense. If it is exceed the input model parameter, so there will be some parameter that we need to decide. A cluster is maximal set of connected dense unit within the subspace. So if it is also dense, okay, this is also another cluster that we can consider. If it is also dense, then we can consider this is as one cluster. So if it is connected, then we can say this is one cluster. The step in the clique, okay, we first partition the data space and find the number of points that lie inside its cell of partition. Okay, so as I mentioned to you, we have this data and then we want to partition. Let's say I want to partition into some grid like this and identify the subspace that contain cluster using the a priori principle. You still remember a priori principle? If you forget, please look at the association. So this is one algorithm. The a priori principle is the algorithm from the association rule. The idea is if the k-dimensional cell C can have at least L points only if every k minus 1 dimension projection of C, which is a cell in the k minus 1 dimensional subspace, has at least L points. So the idea is the same. If, okay, let's say in this data, okay, in this cell, if it is frequent, then I can go to the next level. If this cell is not frequent, then I do not need to go to the next cell. So if a cell is not dense, k minus 1, it means the previous cell or the previous dimension. If it is not dense, then the next dimension will be not dense. Okay. So we can identify the clusters by determining the dense unit in all subspace of the interest and determine connected dense unit in all subspace of the interest. Okay, so the idea is the same with the DB scan. We need to determine the dense unit and we need to identify the connected dense unit. Generate the minimal description for the clusters. It means we need to determine the maximal regions that cover a cluster of connected dense units for each cluster and determination of the minimal cover for each cluster. So we need to find the maximal region and we need to find the minimal cover. Let's see one example. If you do the data visualization, for example, now I have the variable x and then I have the variable salary and then I have the variable vacation. Okay. Now I would like to know which cluster can represent the best. In order to find the clusters, you can make this kind of grid, and then you can make partition 1, 2, 3, 4, 5, 6, 7 like this, and then you can make the partition 1, 2, 3, 4, 5, 6, 7. So the number of partition, it is good if it is the same. After you have those partition, then we plot the data. What is the data? Okay, let's assume this is the data, and find the minimum description for this one. So let's say I have the minimum description is the density should be at least 2. Okay. Then okay, this is 2. This is 2. Okay. This is 2. Okay. This is 2. This is 2. And this is 2. This is 2. This is 2. And okay, the other is 1. Now the same concept of the a priori principle and using the idea of connected principles. If it is here, then it is still connected. This one is still connected, and this one is still connected. This one is still connected with this one is still connected, and so on. Okay, so we apply the density and the connected. So at the end, we have these clusters. Now, I would like to put another kind of clusters based on the vacation and age. So I plot again the data, and then let's say, I have the dense equals to 2. So for every data that has 2, okay, I will consider it as the we choose this dimension. Okay, we choose this one, we choose this one, we choose this one. Okay, and then it is connected, so we disconnected, we choose this cell, it is connected, we choose this cell, it is connected, we choose this cell. Then at the end we have this cell. Okay, with the vacation and age, we have this minimum of the minimal description cells. With the salary, we have this minimal description cells. So we can combine. How to combine those? It means we can look at this one. Okay, the age is between 25 until 45. This one until 45. And the salary is in between 3 until 7. Or the age is in between 35 until 50, and the salary is between 2 until 6. So this is the minimum description for this one. So how can you make the minimum description of this? Okay, you can try. It means we have several description. Vacation between 1 until 3 weeks, and then we have the age is between 20 until 39 or 40. And then we have another condition. The vacation week between 1 until 4. There is another condition, and we have another condition, the vacation between 2 until 5, and the age is in between 35 and 50. Okay, so we call this is the minimal description for these clusters. So dense unit found with respect to age for the dimension salary and vacation. So salary and vacation are intersected to provide a candidate subspace for the dense unit of higher dimensionality. So we have the age here. The age is the basis. And based on the vacation, okay, we have this cluster. Okay, so this is the cluster on the vacation. And based on the salary, we have this cluster. After you have this cluster on the salary and you have the cluster on the vacation, then you can make into one, and we have the cluster or the aggregated cluster between this cell and this cell. So that's the dense unit with respect to its and salary and vacation. So the click, okay, the strength is, yeah, we can automatically find the subspace of the highest dimensionality such that high density cluster exists in the subspace. It is insensitive to the order of the records of input and does not presume some canonical data distribution. And the method is scales linearly with the size of input and has good scalability as the number of dimensions in the data increase. It means when the data is high or the data is big, there is no issue with the computational. It's not that complex. But the weakness, the accuracy of the clustering result may be degraded at the expense of the simplicity of the method. So this method is simple. You just make the grid, you just make the cell. So we do not know whether the clustering result is good or not. But we can just use simple method for making the clusters. The last one that I want to explain is how to evaluate the clusterings. The clustering, it has one concept, which is the clustering tendency. The clustering tendency means assess if non-random structure exists in the data by measuring the probability that the data is generated by a uniform data distribution. So this is a data with uniform distribution. Okay. Can you make the cluster? With this data, is difficult to make clusters. Okay. Now I have another data, A, B, and C. If you look at the data A, is there any tendency to make the clusters? Somehow 50-50. But because okay, I can see this is clusters, but this is not. How about B? B is difficult. There is no clustering tendency. How about C? Okay, we have the clustering tendency. So we call this is the clustering tendency. Based on the data itself, we can easily look at the clusters. Okay, so in the assignment, you need to analyze the clusters also based on this visualization. For example, using the scatter plot. If there is a clustering tendency, yeah, we can say something about the result. One of the assessment in the clustering tendency, we can use the Hopkins statistics. It is to test the spatial randomness by statistical tests. Given a data set T regarded as a sample of random variable O, determine how far away O is being uniformly distributed in the data space. So I want to know if any point or any variable O is far from the uniform distribution. Okay, so you know the uniform distribution is like this one. If the data is far from the uniform distribution, then it may have a clustering tendency. The sample point, let's say we have n points, it is uniformly from D. We need to find the nearest neighbor. The nearest neighbor means I would like to calculate the distance and find the minimum distance. So I also have another point which is Q, or another group which is Q, and I also need to find the nearest neighbor. So the nearest neighbor here, I would like to split into X and Y. What is X? X is a collection of data with the minimum distance from I to any V. And Y is minimum distance from Q to any V. So the Hopkins statistics, it will be the calculation of all Y. What is Y? This is Y. So the total of Y divided by the total of X. So X is this one, plus the total of Y. So I would like to know the proportion of the data, that is not so if this one, the D minus the Qij, minus the Qij, so it means the point where every of this data, this is not in the Qij, it is the minimum into any vertex or any data point. So once we have the its statistics, or we call it, this is the Hopkins statistics, we can use the significant test. If D is uniformly distributed, then sigma xi, this one, and sigma yi will be close to each other, and h is close to 0.5. Okay, so if the value here is close to 0.5, then it may indicate uniform distribution. It may indicate uniform distribution. So if D is highly skewed, yeah, H is close to 0. If H is higher than 0.75, then it indicates the clustering tendency at the 90% confidence level. So yeah, we need to find this kind of Hopkins statistics information. There's also another way to determine the number of clusters. If you look at the k-means, okay, if you look at the k-means, we have the k, and k equals to 2, k equals to 3, k equals to 4, k equals to 5, k equals to 6, and so on. So there is one method named elbow method. It is based on the empirical method. The number of clusters, it is equivalent to the number of data divided by 2n squared for a data set of n point. So it means, yeah, we need to explore the number of clusters until this point. In the orange, you can check the cluster from 2. Usually, if your data is not that huge, it will give you until cluster 8. Or you can explore, or I think in some cases you can explore until 10, the default. But you can increase. In the orange, there is a possibility to increase how many things you want to explore. So in the elbow method, we want to use the turning point. You know what is turning point? It is the curve of sum of within cluster. Okay, so this one, within cluster sum of squares. You still remember the sum of square error. In the k-means, we have the sum of square error, the sum of square errors, and we want to minimize it. Okay. Let me open. If you still remember in this example, what is the sum of square error? This one. Okay. And in this example, what is the sum of square error? This one. So we want to find the minimum when k equals to 2. What if we do the k equals to 3? So we do the experiment for every k. When k equals to 2, this is the minimum. When k equals to 3, this is the minimum. When k equals to 4, this is the minimum. When k equals to 5, this is the minimum. When k equals to 6, this is the minimum, and so on. Now, which cluster is the best? We call it, this is elbow method. You know elbow? This one, elbow. So it means that the ideal number of cluster is when a gradient of the sum of squares get quite low. So after this one, after this slope, so it is slower, 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 slower. So we can say that the best cluster might be 2 or 3 or 4. But in this case, I can say 3 or 4 is the best because the slope is getting slower. This kind of method is very subjective. You can have different analysis. I can have different analysis. So there is no correct answer. Okay. The other way to do the analysis for the clustering is using the cross validation. You still remember cross validation? We learned this one in the classification. We will divide the data into M parts. So if you still remember, we have a set of data and then you can split, let's say M. M equals to 1, 2, 3, 4, 5, 6. Okay, let's say M equals to 6. Use M minus 1 parts to obtain the clustering model. So 1, 2, 3, 4, 5. Let's use this data to create the clusters. Use the remaining part to test the quality of clustering. So you need to use this one as the testing. Test the clustering result using this data. And for each point in the test set, find the closest centroid and use the sum of square distance between all points in the test set and the closest centroid to measure how well the model fit with the test set. It means after I have these cluster results, I will have the sum of square error. You will have also from here the sum of square error. Using this sum of square error and using this sum of square error, usually we will check, okay, use the sum of square error distance between all points in the test set and the closest centroid to measure how well the model fits with the test set. So we need to check only the test set whether it is good or not with the model from this file data. After you have this one, what happens next? Boom. So after you have after you select the 5 as the training and the remaining as the testing, so you can do like the cross validation. You can use this remaining as the training and this one as the testing and so on. Okay. For any k, repeat it m times, compare the overall quality measures with regard to the k and find the number of clusters that fit the data the best. So in the clustering quality, there are two methods, extrinsic and intrinsic. The extrinsic means supervised or the ground truth is available. What does it mean? If you use the MPG dataset, okay, the CAR dataset for your assignment, what is the ground truth? What is the ground truth? The ground truth is the MPG. So we know the target. We know the label. Okay? In the case of the CAR dataset, the label is numerical. But if I want to make it as a categorical, then I change the numerical into the categorical. So there are two ways. You can manually convert from numerical to categorical, or you can use the clustering to generate the category. Because I know there is a ground truth, or I know there is a label, then we can compare the clustering against the ground truth using certain clustering quality measures. If there's no quality measures, we call it PQ. Okay, I will explain it later. We use also the concept precision and recall. So it means we have like this. If the data in the cluster 1, this is the label 0. And this is the label 1, this is in the cluster 2. So you want to check if the original data is in the label 0 and it is in the cluster 0, how many? If it is 0 but it is in the cluster 2, how many? If it is label 1 and it is in the cluster 1, how many data are there? If it is in the 1 and then it is in the cluster 2, so how many of them? We can measure again the accuracy, precision, recall, and etc. The other type is intrinsic. In the intrinsic, it is unsupervised. So the ground truth is unavailable. And we need to evaluate the goodness of clustering by considering how well the clusters are separated. So this is your analysis on the data set of CAR. So if it is well separated, then it is good. And how compact the clusters are. So what is the measure? The measure is silhouette coefficient. So I already mentioned to you the silhouette coefficient, the higher is the better. Okay, due to the time, I think I need to stop here. Okay, so I will continue again to discuss this clustering quality in the next class. Any questions?